Hi everyone, welcome to our video lecture on the continuation for Notes 10.7 dealing with the ratio and the root test. In class, we went over a couple of examples involving the ratio test, but now we're going to be taking a look at a similar test known as the root test. The root test tells us the following. Let's say that we have an infinite series here given by the series for a sub n. Now, if the limit as n approaches infinity for the nth root of the absolute value of a sub n is equals to L, if it's less than 1, then the series is going to be absolutely convergent. On the other hand, if the limit as n approaches infinity for the nth root of the absolute value of a sub n, if it's equals to L, a number that's greater than 1, or infinity, then the series will be divergent. Now lastly, if the limit as n approaches infinity for the nth root of the absolute value of the absolute value of a sub n is equals to 1, then the root test is inconclusive. So you notice here, we have very similar conditions to the ratio test. If L was less than 1, we have something that's absolutely convergent. If L was greater than 1, or infinity, then we have a series that's divergent. And if the limit is equals to 1, then our test is inconclusive. All right, now, I mentioned in class that the ratio test was especially useful if we had a series that had factorials in it. Now, if you have a series that has powers in it, then the root test is especially useful. So let's take a look at a couple of examples here. All right, now, let's see if we can determine the following. Will the series as n goes from 1 to infinity for 2n plus 3 all over 3n plus 2 raised to the n, will this one here be a diverging series or a converging series? All right, so I see a power, but more specifically, I see a power of n. So let's see what happens if I take the limit as n approaches infinity for the nth root for the absolute value of 2n plus 3 over 3n plus 2 raised to the n power. Now this one here in particular wasn't too bad. It looked like a scary problem because we had an nth power, but since we're taking the nth root, we can go ahead and cancel the nth root with the n power. So now we're just going to be left with the limit as n approaches infinity for 2n plus 3 all over 3n plus 2. Now, as n goes to infinity, we can either use L'Hopital's rule or we can take a look at the n behavior. Now, if I take a look at the n behavior, I see that my limit here is going to be equals to 2/3. Now, lucky for us, this value is less than 1, so therefore, we know that our series absolutely converges by the root test. Okay, perfect. That's a great introduction here to the root test. Now, I want to mention a couple of things here in case you might have been confused. Now, I was taking the nth root of the absolute value of something raised to an n power. I want you to remember that, let's say if we have the absolute value of x to the n, this is the same thing as the absolute value of x raised to the n power. So we can always do this type of cancellations. Okay, now, let's go ahead and take a look here at the next example, which is now looking a little bit more complicated because now we have a series as n goes from 1 to infinity for n to the n all over 3 raised to the 1 plus 2n. Okay, so I see a lot of powers here, so I'm going to go ahead and use the root test. But for this one here, since I see an n to the n, I want you to remember the special limits that I asked you to memorize in class. Whenever we're taking the limit as n approaches infinity for the nth root of n, this is equals to 1. Whenever we're taking the limit as n approaches infinity for the nth root of the ln of n, this is also equals to 1. And finally, if we have the limit as n approaches infinity for the nth root of a, that one is equals to 1. So even though this problem might be looking a little bit scarier, well, thanks to the special limits, I think it's going to be okay. So let's go ahead and apply the root test for our second problem. All right, so I'm applying the root test, and I guess I should have mentioned it here. And there we go. So we're going to have here the root test. So I'm going to go ahead and take the limit as n approaches infinity for the nth root of the absolute value of n to the n all over 3 to the 1 plus 2n. Alrighty, so for this one here, even before taking the limit, I'm just going to go ahead and do a little bit of simplification with algebra. So I'm going to be applying the nth root to both the top and the bottom. Now, for this particular problem, since you're just dealing with positive numbers, I'm also just going to go ahead and drop the absolute value, which I guess we could have also done on the previous example. All right, so we're going to have then the limit as n approaches infinity for the nth root of n to the n, okay? Now I'm going to go and apply the nth root to the denominator, but in the denominator, I'm going to be using the trick that we've been using quite a bit. Since I have 3 raised to the 1 plus 2n, I'm going to go ahead and split out this as 3 to the 1 times 3 to the 2n. Alright, so now taking the nth root and continue using the rules of exponents, or in this case rules of radicals, although it's the same thing. Since I have a multiplication inside a radical, I'm going to go ahead and split it up here as multiplication between two radicals. The nth root of, the nth root of 3 times the nth root of 3 to the n. Okay, now, even before taking the limit, I'm going to go ahead and cancel wherever I can. I see the nth power, it can cancel the nth root. I see an nth root, cancel again another nth power. So this is now leaving us only with the limit as n approaches infinity for n divided by the nth root of 3 times 3. Now, once we start to take the limit, we know that this one here is going to be one of those special limits. This one here is going to go to 1. But what about our numerator though? Well, since the n is approaching infinity, unfortunately for this one, we're going to have a limit that's infinity, or in other words, a limit that doesn't really exist. So this one here, the ratio test is telling us that, therefore, our series, I guess I'll put it here, says the limit does not exist, therefore, the series diverges by the root test. Okay, so now let's take a look at 2 more examples here. And again, you might see that they might seem to be scarier, and they look scarier, but let's see if they actually are scarier. Now in example 3 here, our third series is a series as n goes from 1 to infinity for n squared times 2 to the n divided by 3 to the n plus 1. Now you might be thinking that, oh well, this looks very similar to the problem that we just tried before, except that now I am multiplying by an n squared in our numerator. Is that going to change the problem greatly? Well, let's see. Let's go ahead and take a look. Because our previous series diverged, so maybe this next one also diverges. Well, let's go ahead and apply the root test. So we're going to take the limit as n approaches infinity for the nth root for the absolute value of n squared times 2 to the n all over 3 to the n plus 1. Okie dokie. Now, before taking the limit, I'm going to go ahead and use a little bit of algebra first to see what cancels out. Alrighty, so we're going to have here then the limit as n approaches infinity for the nth root of n squared times the nth root of 2 to the n all over the nth root of 3 to the n times the nth root of 3. Alright, so I split up my radicals and notice that I dropped the absolute value. Alright, so what can I cancel here? So I can immediately see that I'm canceling the nth root with the n power here, as well as in the numerator. I can cancel those, but I have a question for you. What would we get for the nth root of n squared? Can we simplify this one here before taking the limit? Well, if you think about the special limits that we saw here, we're talking specifically about the nth root of n, not about the limit for the nth root of n squared. So what can we do? Well, even before taking our limits, we can go ahead and do a little bit of more algebraic manipulation. And the algebraic manipulation that I'm going to be doing here has to do with, once more, the rules of exponents. So remember that if I have the nth root of n squared, well, I know that x to the a raised to the b is the same thing as x raised to the a times b. Alright, so we're multiplying exponents, but since we know that multiplication is cumulative, I can easily say that a times b is the same thing as b times a, so it looks like I could switch the order. X to the a raised to the b would be the same thing as x to the b raised to the a. And that's basically what I'm going to be doing here. If I have the nth root of n squared, well then I can go ahead and easily rewrite this one here as n squared to the 1/2, which I know is going to be n to the 1/2 squared. Alright, so now again n to the 1/2 is this nth root. Oops, I don't know why I said n squared to the 1 over n, because 1 over n is the same thing as the nth root, which is the same thing as n to the 1 over n squared. Okay, so that's basically what we're going to have now. So rewriting this one, we're going to have the limit as n approaches infinity for the nth root of n squared times 2 over 3 times the nth root of 3. Now, once we took our limits, This is the same thing as 1. This is the same thing as 1. Again, remember our special limits, which is giving us then another 2/3, which, lucky for us, it's less than 1. So therefore, we know that the series, as n goes from 1 to infinity for n squared times 2 to the n over 3 raised to the n plus 1, actually converges, and to be more precise, absolutely converges by the root test. So notice here, our series that was similar, it was not converging. This one here was not converging, but as soon as we put in an n squared, it actually did. And oops, I just realized something here. Just to clarify, guys, it was 3 to the 1 plus 2n. So this one here should have been a 2n. There we go, which again, nothing changes. We could have canceled the n. This one here would have been a 3 squared, but again, it didn't change our answer because, well, it was diverging since the limit was still infinity. Okay, now, let's take a look at one more problem here. And this one here again, is looking a little bit scary, but let's see if it is actually scary. So if you were to encounter this series here, what would be a right test to do to see if this one here is converging or diverging? Again, you can go ahead and try different approaches. Maybe you think about a limit comparison or a direct comparison. It might be complicated to think of a nice series to compare this one to. However, maybe the ratio test could work. Maybe, in this case, I'm thinking that the root test might work. And part of the reason for me to choose the root test is because I know that I have the ln, and I know that one of the special limits that we have here is that the nth root of the ln of n, as n goes to infinity, is equals to 1. So if I see an ln, I remember this limit, so I kind of take it as a hint that, okay, maybe the root test can help us. So let's go ahead and apply the root test. So we're going to go ahead and take the limit as n approaches infinity for the nth root of the absolute value of -2 to the k times the ln of k all over k to the 10. Alrighty. So just as we have been doing before, I'm going to go ahead and apply a little bit of algebra here before taking the limit. Now, one thing to note is that for this problem, the absolute value definitely did help us because, well, now we have a -2 raised to the k. So actually, we are dealing with an alternating series, but again, the absolute value is going to come to the rescue in this case because we're testing essentially for absolute convergence. Alrighty. So, rewriting this one here, we're going to get the limit as n approaches infinity, but in this particular scenario here, I'm going to go ahead and once again split up the nth root, but I'm also going to be splitting up the absolute value. Because again, if we have the absolute value of a times b, this is the same thing as the absolute value of a times the absolute value of b. So I'm going to go ahead and take the nth root of the absolute value of -2 to the k, and I just realized that I changed my indices here. So we're taking not the nth root, but instead we should be taking the kth root, because we're taking the limit as k goes to infinity, because k was our index variable. So I'll put in a k here, put in a k, and there we go. Alrighty, now times, well, sorry, I got distracted here, but now the absolute value here, as I mentioned, is going to be coming to the rescue, because I'm going to simplify this one a little bit more in a second, but now we still need to multiply times the kth root of the ln of k, and we're going to be dividing this one here by the kth root of k to the 10. Now, I'm going to use the same trick as I did above. If I have the kth root of k to the 10, well, the k to the 10 could be written here on the outside. There we go. Okay, now, that for the kth root of the ln k and the kth root of k raised to 10, I did not include any absolute values, because again, those quantities were positive, so it didn't really matter. But the -2 to the k though, well, that one's certainly not always positive, so the absolute value is going to come into play. Now, this is a trick that I encourage you guys to use. I have -2 raised to the k. So as you've seen here for this particular section, we've been reviewing a lot of the properties for absolute values or rational exponents, but in this case, I'm going to go ahead and use another property of exponents. If I have -2, I'll put this one here in blue. If I have a -2 raised to the k, this is exactly the same thing as having a -1 times 2 to the k power, which we can go ahead and rewrite here as a -1 to the k times a 2 to the k. Now, if I'm taking then the kth root of the absolute value of negative 2 to the k, I can easily rewrite this one here as the absolute value of negative 1 to the k times the absolute value of 2 to the k. Now, one more simplification here. If I have a negative 1 raised to the k, then I know that this one here could be simplified a little bit more as negative 1 absolute value to the k times absolute value of 2 to the k. Alright, now since we are taking the kth root of all of this, we can go ahead and cancel the powers here. But now we have the absolute value of negative 1. The absolute value of negative 1 is just 1. So we just now essentially have a 2. Alright, now all of this again was, remember, without taking any limits. I'm just going to go ahead and now rewrite the simplified form of the problem as the limit as k approaches infinity. For our simplification, we got a 2 times the kth root of the ln of k over the kth root of k raised to the 10. Now, this is where our special limits come into play. The kth root of the ln of k is just a 1, and the kth root of k raised to the 10, well, that's the same thing as getting a 1 to the 10th power, which gives us our final answer of 2. Now, 2, unfortunately though, is a number that's greater than 1, so therefore the series diverges. So we can go ahead and write here that the series as k goes from 1 to infinity for negative 2 to the k times the ln of k over k to the 10 diverges by the root test. Okay, and this is it. So round of applause, guys. This is the last and final test for whether a series is converging or diverging that we are going to be encountering. Now, in the next chapter, we are going to be applying all of our knowledge for chapter 10 and apply them to, well, as I mentioned in class before, it's an area where we can actually model functions, other sort of functions, as essentially polynomials. But I won't go into too much detail because that's going to be the topic for our next video lecture. I'll see you guys there.